All right, let's do some energy and so spring examples. We've already done energy and work examples. Some spring examples. So here's our first one. 2 kg object, horizontal surface. So we've got a little block. There's my spring. It's been compressed. Okay, so this is like 10 centimeters from where it would normally be. All right, and I want to know what the power is provided by the spring at the moment it's released, the moment it reaches spring equilibrium, and then halfway in between. So remember, instantaneous power best way to do is find force dot velocity. So right when it's released, velocity equals 0. Sweet. So power equals 0. When at equilibrium, that's when it's reached that full 10 centimeter. Guess what? Force, which is negative kx, x is 0. So that means power is also equal to 0. Now this halfway in between, that's the tricky one. That one is not going to be 0. Okay, so I need to find the force, I need to find the velocity. Well, so this is x equals 5 centimeters. So the force is going to be equal to negative kx, which is negative. Actually, so here's the thing about the negative sign here. Let's find the magnitude. The magnitude will probably be easier to deal with. So magnitude of kx, and in this drawing, it's going to be to the right. So k, which is 200 times 0.05, right? This comes out to be 10, right? So the force is 10 to the right. Okay, it's a little easier. So what about the velocity? Well, we got to do energy conservation for that. So we've got kinetic energy initial plus potential energy spring, potential energy of gravity, both initial, right? Work non-conservative equals kinetic energy final plus potential energy of a spring final, potential energy of gravity final. Now, the nice thing about this is that initially at rest, 0. No height change, so 0, 0. The spring is, oh, sorry, that's actually not 0. 0. But there's no non-conservative work, no friction, right? Frictionless, no non-conservative work. So we can get to this and rewrite it as 1/2 k times x squared, x initial, equals 1/2 mv final squared plus 1/2 kx final squared. 1/2s all go away. We get 200 times 0.1 squared plus no 1/2s. Just said no 1/2s. To 2 v final squared plus 200 times 0.05 squared. And apparently if you plug all that in, you get that v is equal to 0.867. And this is also to the right. Right, so that's important because now we have this force dot velocity thing going. So the instantaneous power, right, is going to be the absolute value of 10 times the absolute value of 0.867 cosine of 0, not theta, 0, 8.67. And the unit for that's watts. I don't think we know if we necessarily talked about the unit, but that's the unit for it, okay? All right. This is a little more straightforward. Energy conservation approach. So this is a Nerf gun firing a dart. The dart's horizontal, and how far will it fly before hitting the ground? Okay. So 2-part problem. We've got the part in the gun, the Nerf gun, and then we've got the part flying through the air, and they're attached by velocity. So the first thing I want to do is the in the gun part, right? So we have initial, or we have one kinetic energy initial. You have gravity initial. You have a spring initial. Non-conservative work. Kinetic energy final. Energy gravity final. Spring final. Okay, again, if no kinetic energy initial, starts at rest. There's no change in height, right? The gun is launched, is thrown horizontally or fired horizontally. The barrel's horizontal, and this is probably the worst assumption here. No non-conservative work. It's unlikely. Obviously, there's both air resistance and friction, and this object's light enough that both those might matter. So that's a pretty bad approximation, but whatever. So we have 1/2 50 times 0.1 squared equals, and actually I forgot to say, this is 0 as well, because it's afterwards the spring is completely relaxed. 1/2 0.02 times V squared. Do all that, you get a V final of 8.66, which is just suspiciously like the last problem, but that's okay. And then we do the kinematic. Then we have to do 2D kinematics. So now we've got the second part, projectile part. Projectile part, we've got V initial, or change in X, what we're trying to find. Let's make that a little prettier here. Got change in Y equals negative 1.5. V initial Y equals 0. AY equals negative 9.8. AX equals 0. V initial X equals 8.66. We can find time using the Y values. Right, so change in Y equals V initial Y times time plus 1/2 AY times time squared. You do this, you get time is equal to 0.55. And then we can get change in X is just going to be 0.55 times 8.66, and that is 4.76 meters. Okay, that's probably the simplest example we'll do in this video, but it's just 2 parts. Okay. We got a wagon being released from the top of a hill. So we got some little hill here, and then it goes down, and there's this thing here. Got a little wagon up here. Okay. This is 5 meters. Okay. Now the big thing with this one is this is a non-ideal spring with a force of that. Okay. So how far will it be compressed? Well, to look at this problem, right, we need to do conservation of energy still. Right. This is still kinetic energy initial plus potential energy of gravity initial, potential energy of spring initial, non-conservative work, kinetic energy final, potential energy of gravity final, spring final. Okay, let's make this height h equals 0 down here. That means potential energy of gravity is 0. Okay. Kinetic energy final, max compression. How far will it be compressed at max compression? Velocity 0. Starts at rest, 0. Spring, not compressed to begin with. No friction, right? There's probably a little bit of friction, but because it's on wheels, we can probably say that it's not going to be a big deal. So that's 0. So I've just got this. So potential energy of gravity, this is 20 times 9.8 times 5. This is equal to the potential energy of a spring. But how do I get the potential energy of a spring? Potential energy of a spring, right, is equal to the negative integral, or negative work done by that spring, right, which is the integral of the force of the spring dx, or dx. Yep. Okay. The integral of this is that's not work at the spring there. And this should be an equal sign. Okay. The integral, right, is going to be negative, right? So negative work, negative times the integral of f, right? The magnitude of f, magnitude of ds or dx, in this case, times cosine of the angle between them. So as this compresses, right, the maximum compression is dx is that way, it's compressing that way, okay? The force is this way. This is a negative cosine of 180. Okay? So that's going to equal negative, the integral of negative, but it's the magnitude of it, right? So we did magnitude, negative, all right, 1000 x to the third dx. Okay, that is negative, and the integral of this, right, we add 1 to the exponent, and then divide by that exponent. So it's going to be negative 1000 over 4 x to the fourth, which is just 250 x to the fourth. This is 1/2 times 250 x to the fourth. This is 980, and I realize this is actually wrong because I didn't do the 1/2 there. So my answer is wrong. So give me 1 second while I find out what the actual answer is, because apparently I'm not good at this. 980 over 125 to the 0.25. X is equal to 1.67 meters. Okay. Alright, so nonlinear spring. Alright, take the integral of it. That gives you the potential energy function, and then you can plug it in there. Alright, now the piece de resistance. This is a pain in the butt problem. But we're going to do it anyways. So we've got a slope. 30 degrees. We got a block, top of the slope. We then have a spring set up at the bottom here, and this distance is 2 meters right there. Now, it's also going to compress a further distance x, and I want to find that x. How far the spring will compress before it stops. Okay. Now, this in itself is already kind of a pain, but we also have friction. So really piling it on here. But we still start the same way. Kinetic energy initial plus potential energy of gravity initial, spring initial, plus non-conservative work, kinetic energy final, potential energy of gravity final, plus potential energy of a spring final. Kinetic energy initial, 0, starts at rest. Kinetic energy final, max compression, 0. Potential energy of gravity initial, that's going to have a height. In fact, that's going to be some sort of height like this. Okay, so let's say mgh initial. Well, we can just say h because I find that as h. Potential energy for spring initial. Oh, that's 0. Non-conservative work. I got the work of friction. That's equal to potential energy of gravity final, 0. We're making that height final. And potential energy of spring final, that is going to be 1/2 k x squared. Doesn't look so bad right here. Okay, this is we've reduced it as much as we normally do. Here's the thing where it gets a little tricky. We need to get all these variables in terms of x. So h, first off, h over this distance, 2 plus x, equals sine theta, or sine of 30 degrees. We know what this angle is. So h over 2 plus x, That means that I can replace h with sine of 30 times 2 plus x. So this is 9.8 times 2 plus x all times 1/2, which is sine of 30. Friction. Work of friction equals the force of friction, magnitude of that, times the distance it goes, which is 2 plus x, times cosine, right, of 180. And it's 180 because this is, right, the path, the s, this is the force of friction. Okay? And we have to do 2 plus x because friction keeps acting. Even though it's hitting the spring, it's still rubbing against the ramp there. And force of friction we know is 9, so this is negative. Force of friction is 9.8 times 1 times cosine of 30 times 0.2, all that times 2 plus x. Whew. So this is minus 9.8 times 0.2 times cosine of 30 times 2 plus x. And then we have equal to 1/2 kx squared. And that part's easy. That's just 1/2 times 150 times x squared. Now, for all of this is like a hard problem, this is actually really, I mean, it's just, you got to solve it. It's a quadratic. Put it into Wolfram Alpha, put it somewhere, and you can get the solution out. And if you just plug all that into the calculator, you get 0.218 meters is how far it gets compressed. All right, that's it.